In this video, we'll be finding factors and zeros of polynomial functions. Let's start with a quick review of what we already know. Here's a quadratic function, f of x equals x squared plus 7x plus 12. We know that we can write it in factored form, x plus 3 times x plus 4 in this case. Once we find the factors of the function, it's easy to find the zeros of the function. We set each of these factors equal to 0 and solve. In this case, we have x equals negative 3 and x equals negative 4. We can see this relationship between the factors and the zeros of the function. And when we look at the graph of this function, we find x-intercepts at those zeros, negative 3 and negative 4. We also know this graph is going to be a parabola because we have a degree 2 polynomial. We know that the end behavior has both branches going up in the positive y direction, and we have one turning point. So for the rest of the examples, we will be finding factors and zeros of functions, and at times identifying zeros as x-intercepts on the graph. Another idea that we'll use in this video is that factors can be evenly divided out of polynomials. We do know that this trinomial is factored as x plus 3 times x plus 4, but we're also saying that if you divide one factor out from the polynomial, you'll have a remainder of 0, and the quotient will be another factor. And we can accomplish this division with long division or with synthetic division. Remember, on this side, up here is our quotient, the dividend and the divisor. With synthetic division, our divisor is really the 0 of the factor. Back here is our remainder, and these numbers are the coefficients of our quotient, in this case, x plus 4. So now we'll be dealing with some examples where we want to find all of the factors and zeros of the polynomial. This usually begins with our old factoring strategies. When those don't work, then we'll examine other techniques using graphs and synthetic division. In this example, first we're always looking for the GCF. So in this example, a 3x can be factored out from each term. That's leaving us with x squared plus 4x plus 4. We can factor this trinomial further as x plus 2 times x plus 2. The function is now in factored form, and what we're interested in is that all of our factors are linear, at least the factors that are not the x out front. It's okay that we have an exponent there. If we do, it definitely tells us about our multiplicity, but we do not want to have x squares or x with any degree higher than 1 inside of our parentheses. So we have it factored right now. We can talk about what the zeros would be. If we set each of these factors equal to 0, 3x equals 0 basically tells us that x has to equal 0, and each of these other factors lead to solutions of x equals negative 2. So there are the zeros. Now let's talk about what the graph of this function would look like. We know it's an odd degree, so the end behavior are doing opposite things. One branch is down, one branch is up. We have a positive leading coefficient, so the graph will begin in quadrant 3, or in the lower left, and work its way up towards quadrant 1, or the top right. We know that our zeros are intercepts on the graph, and where we have these two with a multiplicity 2, we're going to see the graph only touch at the x-axis, and at x equals 0, we will see the graph cut through the x-axis. There we have it. Tangent at x equals negative 2, and cuts right through at x equals 0, and we are going from lower left up, eventually up to upper right. Next example, can we factor this? Well, anytime I see 4 terms, I'm thinking factored by grouping. From the first pair of terms, do we have a GCF? And from the second pair of terms, do we have a GCF? The first pair, x squared, leaves us with x plus 1. From the second pair, we can factor out, I'm choosing a negative 9 to get the signs to match up, and an x plus 1 matching in parentheses from both pairs. So the x plus 1 is one factor, and the GCFs x squared minus 9 become the second factor. But we should spot a difference of squares that we could factor further, and that will leave us with our 3 linear factors, and we can start to work in this pattern that our degree of the polynomial tells us how many linear factors we should have and how many zeros we have. We know it won't always be that many x-intercepts, though, because complex zeros don't show up as x-intercepts on the graph. We'll see some of those later. But from these factors, can we find the zeros, -3, +3, and -1 for the zeros of this polynomial function? Let's again think about the graph. So another degree 3 polynomial with a positive leading coefficient, but we see 3 different x-intercepts this time. So we'll have that cubic pattern, but we'll see intercepts at -3, -1, and +3. Here's the next example. F of x equals x cubed plus x squared minus 14x minus 24. Now this one cannot be factored with factor by grouping. If we do try to pair them up and look for a GCF, we will find that our quantities in parentheses don't match, and we will not be able to do factor by grouping on this one. So when this happens, we have to turn to our other pieces of knowledge. We can look at the graph to decide if we have real zeros or complex zeros and how many we have. We can look at the graph to get a good idea of what those zeros might be, and we can use synthetic division to confirm that we do have a factor or a zero if we have a remainder of 0. So first, the graph. It looks like we do have zeros at -3, -2, and +4. But I don't want to rely on the graph because we could be off by just a little bit and not be able to tell. So we're going to use the graph for good guesses, and then we'll confirm with synthetic division. So just a little number line with a reminder that those were the zeros that we saw in the graph. Let's start this synthetic division with the 0 at +4. And remember, synthetic division is we're bringing down, multiply up, add down, and so on. We're looking for a 0 remainder, which we did get. So x minus 4 is a factor, and 4 is the 0. This was degree 3, so we're aiming for a total of 3 zeros, 1 down. Now, we have some options. We could try synthetic division again with our quotient. If I tried -3, it would look this way. We'd get the 0 remainder. I'm left with x plus 2 for the coefficients, and that leads us to our last 0 at -2. But the way that I'd like to finish up these problems is to stop the synthetic division once we're left with a quadratic, because at that point we can either factor it with the techniques we've been using, or we can solve it with quadratic formula. In this case, the coefficients tell us that we have a quotient of x squared plus 5x plus 6. Definitely we can factor as x plus 2 times x plus 3. These factors will lead us to our last 2 zeros at -2 and -3, so the graph was very accurate in what it was trying to portray with where those x-intercepts were. Now completely factored, our polynomial has these 3 linear factors and these 3 zeros. Here's our next example, x cubed minus 7x minus 6. Well, don't jump right into factoring trinomials because we have x to the third, not an x squared. So let's look at the graph. Interesting, it looks like zeros at +3, -1, -2. Let's use synthetic division to confirm that those are the zeros. Let's start with +3. Remember about synthetic division, we need to have a spot for every exponent from highest exponent down all the way to the constant. So we have 1 from the 1x to the third, 0 because we have no x squared, -7 from x, and -6 the constant. So the synthetic division looks like this. We get that remainder 0, and that's great. So we have confirmed that 3 is a 0, and x minus 3 is a factor. Let's use these coefficients of the quadratic to find our other factors. We can factor this one, x squared plus 3x plus 2 is x plus 2 times x plus 1. So we have all 3 factors, and the zeros at 3, -2, and -1. Next example, x cubed plus 5x squared plus 3x minus 6. Now again, when I see 4 terms, I like to try factor by grouping, but it's another example where factor by grouping will not be successful. So I'll take a look at the graph. It looks like, at first glance, maybe at +1, -2, -4, but I see that's not really on negative 4 there. Also, we mentioned once about the rational zeros theorem, which says basically that if your polynomial has leading coefficient of 1, then you look at the factors of the constant, and your zeros will only be factors of that constant. So even if it was looked closer to negative 4 is not a factor of 6, so it wouldn't make sense to think negative 4 in this case. Negative 2, I think, is going to be my try, and even a closer look makes me think that's not really on positive 1. It's a little bit less than 1, so we're going to have to try synthetic division with negative 2. Setting it up, the 0 at negative 2, and our coefficients positive 1, 5, 3, and negative 6. Synthetic division, we're bringing that one down, and the whole multiply up, add down. We do see remainder 0, so good. X plus 2 is a factor, and negative 2 is the 0, and these coefficients give us our quotient. Now we have to figure out the two factors from this expression right here, and our old methods of factoring are not helpful on this trinomial. So we should go to quadratic formula instead. We know the close relationship between factors and zeros, so we don't always have to find the factors first and then get the zeros. We can find the zeros first, solve the equation, set it equal to 0 and solve, and then once we have the zeros, we can figure out what the factors were. So these coefficients are a, b, and c. We'll plot them into the quadratic formula. A little simplified, negative 3 plus or minus radical 21 over 2. So those are the last two zeros we're looking for. Since it's degree 3, a total of 3 zeros. We had one at negative 2. Here are the second and third. They're irrational numbers, but still real. That's why we see them on the x-intercepts. If it had an I, that would make it complex. So the radical is okay in terms of it will still be an x-intercept. So now that we have our list of zeros, we can write what the factors were or are, and basically we're using the idea that zeros show up in a factor as x minus the 0. And x minus negative 2, we'll know to change that to an x plus 2. There's that relationship between factor and 0. And what I'll do for these, if I have to write the factors, is basically just open up the parentheses and put an x minus the one irrational number and x minus the other irrational number. One with the plus, one with the minus. Here's our next example, and we're starting to see a trend that we encounter polynomials that we cannot factor using techniques that we've learned earlier. So we're getting used to, right away, taking a look at the graph. We even can say some things about this graph based on it being an odd degree with a positive leading coefficient. We know the end behavior of this graph, like a cubic graph. And any odd degreed polynomial, its graph must go through the x-axis at least once. So when we look at the graph, we will find at least one x-intercept. Here's the graph, and it turned out that we had only one x-intercept. So degree 3, we're expecting a total of 3 zeros, but with only one x-intercept, it means we've got one real 0 and 2 that are complex. And this one appears to be at negative 3. It's really the only thing we can try, so hopefully we will be successful. We know that in terms of being successful, we're looking for division that has 0 remainder. So we're setting up the synthetic division, negative 3, bring down, multiply up, add down, the whole bit. We do get that remainder 0, so negative 3 is a 0, and x plus 3 is a factor. Our quotient is quadratic, so let's use quadratic formula on that. Plugging into quadratic formula takes us to negative 2 plus or minus square root of negative 16 over 2. So we do end up with a negative in the radical, and we expected that because we knew we were headed towards two complex zeros from those missing x-intercepts. Let's simplify further. Let's bring the negative out of the radical and make it an I, and let's also make the 16, the radical 16, into 4. At this point, if you're thinking simplify, we can, because we can divide evenly from all three of our terms. Dividing everything by 2 gives us negative 1 plus or minus 2i as our two complex zeros. So the list of the zeros, we've got all three, one real at negative 3, 2 complex at -1 plus or minus 2i. If we were to write the factors, the -3 would be x plus 3. These complex numbers, I'll just take the same approach as I did with the irrationals, x minus each complex number. And you can choose to distribute the negative sign if all these parentheses is just excessive looking to you, or you can leave it as is. Here's a good example for you to try. So pause the video, grab pen and paper if you don't have it already, and your graphing calculator. Try this one out, and then restart the video. We'll go through the answer. We've got degree 4 this time. We know our end behavior on the graph. We'll see our branches both going up because we've got a positive coefficient, and they're doing the same thing because the degree is even. We may see some turns in there. We may not. We're not going to see a ton. At most, we're going to have 3 turning points. Old methods of factoring, no chance on this one. We've got 5 terms. I'm headed straight for the graph. And this looks interesting. Positive 4 looks like it could work. -3 or somewhere in between -3 and -4. So I see a couple things to try. I'm going to do positive 4 and -3. So back to the polynomial, I have a quick, crude little sketch just to point out my curves and the intercepts at -3 and 4. Those are the ones that I'm going to try synthetic division with. Starting with -3 gets this result out of synthetic division. So we got the remainder 0, good, and we have our quotient down here. You know, I'm actually still on the lookout each time for can I do some factoring. So I look at these 4 coefficients and think, could I do a factor by grouping? But we cannot, so I'm still stuck on the synthetic division again. This time we'll use the positive 4, and this is going to give us another good result, remainder 0. So we confirmed those 2 x-intercepts are zeros right at -3 and positive 4. Our other 2 intercepts must be irrational numbers, and we can get that sense from this quadratic that cannot be factored. So dumping into quadratic formula and a little bit of simplify, -1 plus or minus radical 6 as the 2 irrational zeros for this polynomial. Another example, another 4th degree polynomial. Let's take a look at the graph. This is a pretty interesting looking graph. We don't get much to work with in terms of x-intercepts. It looks like we're going to try -1, but also notice that this intercept is tangent. It's not crossing through, so we have to have a degree that is even. So perhaps multiplicity 2 at this x-intercept right at -1. Now, one approach that I could use would be like I've been doing so far. I'll try synthetic division with -1. I'll confirm that I have a remainder of 0. I'll do synthetic division again with that -1 because I got to get both of those repeated factors out of there. And then I'll be left with degree 2. I can do quadratic formula and finish, but we like to keep things interesting and change it up once in a while. So I'm going to take a guess that -1 is a 0 with multiplicity 2, just based on what we saw on the graph. It looked like there was an x-intercept there, definitely tangent, so I'm going ahead and saying multiplicity 2. That means that our factors would be x plus 1 and x plus 1, or x plus 1 with the multiplicity 2. I can take this and multiply it out, x squared plus 2x plus 1, and I know this is a factor of my original polynomial, so I'm just going to divide it out with long division. Because I know I have a factor, I'll divide it out, I'll see a remainder with 0, and my quotient will be the degree 2 factor left over. Okay, and a good opportunity to show what happens when we need to do long division with 3 terms in our divisor. It's basically the same approach. We're looking at our first terms. In this case, x squared times what term will equal x to the 4th, and we'll come up with x squared. And each time we come up with a term in the quotient, we'll multiply back down. And with 3 terms in the divisor, we just multiply back down to each of those 3. X to the 4th, 2x to the 3rd plus x squared. This is a subtract. I usually like to flip signs and add, but we're dealing with all positives here, so this is not too bad. I can subtract those and not be too concerned about my signs. Bring down the 3x. I'll even bring down the plus 1. Might have to use it here. X squared times what will equal x to the 3rd, so that's positive x. and multiply back down each of those 3 times. We're going to subtract and bring down that plus 1. And last move, we're going to put a plus 1 up in the quotient, multiply back down, and subtract, and we get 0 remainder. And we were expecting that because we had factors, but it just confirms what we were suspecting based on what we saw in the graph. And now this quotient we know is the leftover factor, but we want to get down to linear factors. We know this started out as x plus 1 and another x plus 1, but we've got to break this factor down into linear factors. It is quadratic, so I'm going for quadratic formula. And we've seen one similar with all a, b, and c equal to 1, left us with negative 1 plus or minus I radical 3 over 2, or if you split it up, it was a negative 1/2 plus or minus radical 3 over 2i. So those were the 2 complex zeros to go along with our 2 real zeros, basically the 0 at negative 1 that has a multiplicity 2.